Welcome back to AP Physics 1 review. In this video, we'll be covering Unit 3 of the AP Physics 1 curriculum, which is work and energy. If you haven't watched the last two videos on kinematics and forces and dynamics, I would highly recommend that you go to my channel and watch those videos first, because those explore and review essential concepts that will be used in this video. Anyways, let's get on with it. We're going to be moving pretty fast today as this is a review video, and we're not going to be going too into depth into derivations and problem solving. This is just what you need to know for the AP Physics 1 exam that's going to come up in a couple weeks. Let's get on. First up is work. Work is defined as the transfer of energy in and out of a system. And the primary equation for work is work, defined by capital W, is equal to the force applied on an object, the displacement of that object, denoted by D, and theta, which is the angle between the force vector and the displacement vector. Now, the reason why we're multiplying F and D by cosine theta is because we only want to consider the component of the force that is parallel to the displacement. Now, work is positive when the force vector and the displacement vector are in the same direction. Work is negative if they are in opposite directions, and work is zero if they are perpendicular, which means, and this might come up in some of your MCQs, the centripetal force does no work because it is perpendicular to the displacement vector. Now, here are the common types of energy you'll see on the AP Physics 1 exam. First up is kinetic energy, which is energy by virtue of the motion of an object. It is equal to K is equal to 1/2 mv squared. Okay. Then, another type of energy is gravitational potential energy, which is the energy given by virtue of an object's position in a gravitational field. So there are two main equations that you're going to see on the AP Physics 1 exam. And you'll have to be able to differentiate in problems, MCQ or FRQ, when to use either one of these. So to use the one on the right, which is UG is equal to mgh, gravitational acceleration, or g, has to be relatively constant. So if you're staying on like a single planet, or if you're on Earth, you'd probably want to use this equation on our right. But if we're dealing with celestial objects and orbits, it's best to use the one on the left, which is U sub g is equal to negative g m1 times m2 over r. Finally, one that you'll probably see in relation to oscillations the most often, which is a future unit that I'll cover, is elastic or spring potential energy. Now, is currently in this picture I have here, it's the variable used to denote elastic spring potential energy is P elastic. However, PE elastic, However, it is also denoted by U sub S on AP Physics 1 exam. Now it's equal to 1/2 kx squared, where k is the spring constant of the spring, or force constant it is also called, and x is the displacement of the spring from its initial position, which is just how much it's stretched or compressed. Next up is the work-energy theorem that ties work and energy together. Now, this theorem states that change in energy is equal to work, and it's derived from the expression the initial energy of a system plus work is equal to the final total energy of a system. Now, this is a very powerful equation because since work is equal to force times displacement cosine theta, it actually is able to tie motion with without having the need for acceleration and time to solve for certain problems, which is very useful. And as you saw earlier, the conservation of energy just means that in a closed system with no net external force, energy is conserved, or mechanical energy is conserved. So the total energy of a system initially is equal to the total energy of a system finally. However, some common net external forces or non-conservative forces that can lead to mechanical energy not being conserved are air resistance and the force of friction. So, and then there's power, which is like honestly pretty simple. Its power is defined by the rate at which work is done on a system, or P is equal to W over T. Now, another equation for power that can be used is P equals to the force times velocity, because work is equal to force times displacement over T, and D over T is equal to velocity. So, but both of these equations will be very easy to spot when to use them. Power problems are very easy on the AP Physics 1 MCQ section, so I wouldn't worry about this one. Some common energy problem types are to find the work done by a force at an angle, find the final velocity of an object or the work done on it, find the final velocity or final height of an object, and find the energy lost to friction or non-conservative forces. And then there's just power problems. So for the first one, to find the work done by the force at an angle, you just have to use the definition of work, which is W is equal to FD cosine theta. Maybe you might have to find the angle, all this stuff. Just rearrange. It's not that hard. Those ones are super simple, probably won't appear that often. Then, what might appear more often is finding the final velocity of an object or the work done on it. So all you'd have to use is the work energy theorem to find the final velocity of the object. Remember, energy initial plus work is equal to energy total. Use that equation and you'll be able to find final velocity, final height, or anything. Now, another similar one, which is to find the final velocity or final height of an object, which looks pretty similar to the first one, or the one I just mentioned, is one where there's not any work done on the system, but in fact just a change in position or elevation. So for example, a ball rolling down and up a ramp, or a ball falling, all that kind of stuff. You can use the conservation of energy, which is energy initial is equal to energy final, to find different unknowns. For example, an initial height as well could be possible on the Physics 8 MCQ, or initial velocity, not just final velocity or final height of an object. Then, this one's a bit more complicated, it is to find the energy lost to friction or non-conservative forces. So this one are typically more complicated because they require a couple more extra steps, mainly just because this problem type is usually used in more complex manners than the other ones. Like sometimes you're missing more values, sometimes there's more stuff going on. But yeah, all you have to use is just the work energy theorem. And just to find the force or coefficient of friction, same thing. You just have to break down the work energy theorem into smaller parts. For example, work is equal to FD cosine theta, then break the force to friction into the coefficient of friction times the normal force, and so on and so forth. And then there's power problems where you just plug and chug. That's it. Anyways, guys, that's it for the work and energy AP Physics 1 review. Next up will be linear momentum and collisions. Thank you guys for watching.